So directional control valves, these are pneumatics, but you have to understand that we have the same type of valves basically in hydraulics. So there's two big things different. Normally, if we're not using our pneumatic pressure, we're going to block it off so that we don't lose compression. Normally, if we don't use hydraulics, we send it back to the reservoir. So it's a big difference. The valve will do this. So what we're going to do with the directional control valve, we're going to do what? We're going to stop the fluid flow. We're going to allow it to flow, or we're going to change its direction. Three things these valves are going to do. So in your house, basically all you do is, we do have what we call proportional valves. We're not going to get into those. I don't think that's covered in the book, where we can actually adjust the valve, electronic or electrical. We can operate them manually, which is basically a lot of your valves in your house are manually operated, but you do have some that are not manually operated. They're automatically operated. How many people got a washing machine? Or you got a valve in there that automatically does what for you? Turn the water on, turn the water off. So that would be automatically operated. And you got an ice maker, you've got valves in there that are automatically operated. You've got a dishwasher, and the toilet is automatically operated. So except when you flush it, so that's kind of a combination. When you flush it, that's one valve that you operate manually, but then it shuts off water automatically. Operates manual automatically. So manually we're familiar with. Automatically we got a little feel, but when we do it automatically, we're going to do it on mechanical devices. So your commode, that is a mechanical device that shuts it off and slow it. We looked at that. Hopefully everybody here by now is inside the tank of the toilet. When you see a flow in there, that is a mechanically operated valve, right? Then we got to have electrical operated valves, and then we can have valves that are operated by fluid. We call these pilot valves, and we'll look at that as we go along. So when we move into automatic operation, we're going to run in all our valves that we have are either going to be in this class are going to be either mechanically operated, manually operated, or mechanically operated. We don't have any electrically operated valves. Alright, so the way we identify a valve, and this slide don't show that, I know that, okay. The way we identify the valve is by the number of ports, which technically we call it waves. So that's the wave that is. So instead of saying a 4-port valve, we say a 4-way valve. Are we okay? And then we generate it by the number of positions that valve can be put in. Basically, we have 2 positions. We can have ports. Got to have at least 2 ports, right? Of 2 ways. And we can have up to 5. Then the valve is going to be able, we're going to be able to put the valve in multiple positions. A minimum of 2, a maximum of 3. So we have ports from 2 to 5. Port numbers from 2 to 5 are ways and up to 2 or 3 positions. So your valve that's operating that's operating your washing machine. It has 2 ports, right? And it has 2 ways, and it has 2 positions. See if open and close. By the way, this usually always gives people problems that come out of electronics. That when we talk about a closed circuit, we say that's a complete path to earthquake. When we talk about an open circuit, it means it's an incomplete path to earthquake. Fluid power guides us through top. So if you open a valve, the water flows. If you close the valve, the water stops, or the fluid stops, right? So that's going to be a little funny. So your normally open and your normally closed valves are going to be completely different than your normally open and your normally closed contact. Then we have the way we control the valve. We're going to control it by a poppet, or we're going to control it by a disc, or we're going to control it by a spool. Most of your valves that you use in fluid power, not your house, but industrial fluid power are going to be spooled up. Most of them, unless they're manually operated. Most of your manually operated valves are going to be either gate valves or operated by a disc, something like that. Are we okay? Mechanical, electrical, manual, or what we call pilot operated. Pilot is a valve that actually uses fluid to open and close the valve. So pilot operated valves is going to be controlled by the fluid. Of course, we're familiar with manual valves. Electrical, if we went over on the manufacturing line, when we went over it last Wednesday, all those valves over there, not all of them. And we have the main valve, that's a manually operated valve, which is up on the, where we can actually turn the pressure off and on, right? So we have normally, we have a way of disconnecting the power. It's very, very important, especially in investment. Because if I'm going to go out there and work on something, I'm manually work on it. And what we want to do is we want to disable the power. Always. We're working on it. Now, operating and troubleshooting, odds are you're going to have power on. When you go out there and actually work on it, we need to have the ability to turn that power source off. We don't have any locking tags over here, but we do over on this side. So normally what we do is when we're working on it, when we're out there doing maintenance on a unit, then what we're supposed to do is we're supposed to locking tag. So you got to put the locking tag on this power source. Well, what happens is a lot of people will disconnect they'll lock out the electrical power source, but they won't lock out the fluid power. That gets people in trouble a lot. You really get hurt about fluid power too. Of course, you can't get electrocuted about fluid power, but you can definitely get hurt. So all our lines over there has the ability to lock and tag all power sources. And if we went over there and looked at the big FANUC robot over in the other room, you'd see it's got a lockout on all the power sources. Pneumatic, your hydraulic, your fluid, all your fluids, and also electrical. You can lock it up. But all the other valves are all other valves on the Pesco line are electrically controlled. So see, look, these are the valves they talk about. These are all manually controlled valves. We have gate valves, globe valves, needle valves, plug valves, and ball valves. And you'll run into all these out in disconnects. Your house uses a lot of ball valves. Your house uses a lot of globe valves. Don't use any needle valves in your house. Gate valves, ball valves, we run into those. Odds are that you got to disconnect. Normally a globe valve or a needle valve, you get a mechanical advantage by a screw. Screw's got little fine threads on it. So on those valves, you have to turn them multiple times to open and close. Your ball valves, these are going to be basically 90 degrees to open them. They're real straightforward. If the handle's in line with the pipe, then it's going to be open. If it's to the side, it's going to be closed. And So ball valves, you can turn those things off and on with just a quarter turn. Well, you get your mechanical advantage with the length of the handle that you use to turn it, right? I can put those on my sink. So sink or outside faucets, you get your mechanical advantage by the spacing on the screw. So what you're doing is you're actually turning the screw, a threaded screw, and the narrower the thread, the more you have to turn it, that you get the mechanical advantage. So gate valves would be the same way. Y'all see a gate valve. Globe valve, this is most of your faucets in your house are globe valves. Ball valves, we use those a lot in pneumatics because the pressures are so low. So we'll go over there and we'll look at our disconnects that come from the roof. These are all ball valves. But these are all manually operated valves. You know, we've been using manually operated valves for a long time. I guess the flapper on your commode would be considered to be a gate valve, right? So this just shows you the different ways we can cut off flow. I think this is right out of the textbook. This was actually scanned out of the textbook. What page this is on, I'm not really sure. Oh, okay. So we okay? Any questions here? Yes, no? So we can operate the valves. We can operate them manually. We can do self-activated called pilot valves. We can do mechanical. All our valves that we're going to use are going to be mechanically operated. We can use it electrically with a device called a solenoid. I might have my place solenoid over here. Or we can do it pilot operated. These are going to be with pressure. So self-activated, we'll look at some of these. One of the valves that are self-activated, we have what we call a check valve. What's that? Check valve. Good guess. So I've got a check valve. Hopefully you got a check valve on your house. Because what would happen if you didn't have a check valve, if the water company came out there and turned off your water, and your water's up here, what would happen to all the water in your house? It'd drain out. And then they would turn the water back on, and you'd have to pay for the same water twice. So what does the check valve do? But it only lets water flow. It only lets fluid flow in one direction. So it blocks. So that's going to be a self-activated valve. We have a valve called a shuttle valve, which is really neat. It prevents two stations from operating the same valve at the same time. So that would be awful, me over here doing it, right? And I'm putting the valve in this one position. And old Charlie down there decides he wants to put the valve in the other position, and you're out there doing something. So a shuttle valve is an automatically controlled valve, which means if it's got pressure on this side, the other guy can't do what. Yeah, cut that out. So these are self-activating valves. These are valves that automatically. So a check valve would be a self-activated valve. A shuttle valve would be a self-activated valve. Mechanical valve, which means we're going to turn a knob or we're going to bump against something. We're going to do it that way. So when we get over there, our valves are going to be manually operated. All our valves over there. Nancy didn't get the solenoid package because those were very, very expensive. All the valves over on the manufacturing lab, except for the disconnects, those are electrically operated valves. Now, electrically operated is pretty big because now we can start moving toward automation, right? And then the pilot valves, these are going to be operated by the fluid, or they're going to be assisted by the fluid. Pilot operated. So what pilot operated is we use the pressure of the fluid to change the position of the valve. That makes sense? We'll see that. So what we've got an operator in there. So a spool is going to be basically, maybe where it, so a spool is going to be something that's got some notches cut in it. And what we do is, and it's called a spool because it's look kind of like, and then we got different ports up here, and then we either push that side to cause the spool to shift, or we can push on that side to cause it to shift. Well, what do we need to push on? Pressure. We need pressure. Well, what's there? I mean, so my fluid has pressure. So why can't I use that fluid to change the position of the valve? Okay, does that make sense? Now what we'll do is we'll use something else to do that. The problem is when we get into hydraulics, your valves get so big that it would be even hard for you to operate. So what you would do is you'd have another valve that you control maybe manually. It's a little valve. And what you do when you control the little valve, it puts pressure into the big valve that shifts its direction. So normally what we do is we have another valve that controls the pressure that moves changes the direction of the big valve. And we run into that a lot. Solenoids can't generate a lot of pressure. So when you get into these big pneumatic valves, they're going to be what the solenoid will do. It'll open up the pressure port. The pressure comes in and causes the valve to shift. So that's a good question. So what we're going to do on these guys is they're going to be actually operated by pressure. Of course, we're going to control that pressure somewhere else, right? So these are going to be solenoids. So solenoids are nothing but anytime we put current through an electric wire, it generates a magnetic field. And I don't have a power supply with that, so I can show you the solenoid. By the way, what we do to represent the symbol. So what we do is we've got to represent a fluid circuit. So we call it a circuit. So in fluid power, a circuit is a complete path of fluid. What it does, it consists of a pressure source, it consists of controlling that pressure source, right? And then actuators something out there doing that. What about the line? Well, that's part of the system, but it's not part of it. So you're right. So what we have to do is we have to get, so basically you're right. So what we have is we have a pressure source, right? And then we would have control. And then we would have an actuator. And then what do we connect everything together with? But what we want to do is, when we represent a circuit, so that would be what we call a circuit. Instead of us trying to draw a picture of everything that's out there, we call them pictorial diagrams. So you go out by and you get a pictorial diagram that shows you how everything looks. Well, for the novice, that works out because, we got plenty of room and all this kind of stuff. But when we get into technology, what they do is they start representing circuits instead of using particular facts or devices. They use symbols to represent different devices. So what we do on control valves is we represent them with these little blocks. And we use one block for each position. So when I see these two squares, that means that this valve has two positions. If it had three positions, we would have three blocks. So we'd have two outside and we'd have one guy in the center. So we use these blocks to represent the actual valve itself. And then we use different things to represent the actual ports. So when I come out here and look, I see two lines extending out past the blocks. So when they extend out past the blocks, that means this would have two ways. And it would be two positions. That makes sense. Now we would call this valve is, then the valve is going to be in a what we call an initial position. So that means I could come over here and this could be my pressure This could be my working port, and if it was in that position, we'd call this right here, we'd say it was a normally closed valve. Because in fluid power, if the valve is closed, we have no flow, right? If we have no flow, we have no pressure. If I understand that. So whether it's a normally open or normally closed valve would depend on the initial position. Normally we draw the initial position over on the right hand side. So this right here would be what we call, this would be a normally open two position, 2-port valve. Does all that make sense? Yes. This would be normally closed, yeah. Normally closed. This would be what we call a normally closed. Now the problem is, why they did it this way, I have no idea. Is what we start off with is we start off with the number of ways. So I come over and I put 2. And then I put a slash, and then I put the number of positions. And then we say this. So we call this a two-way valve. So it's kind of strange because the ways come first, but you use the ways after the position. Does that make sense? So if I had a 4, so here we'd call this a 4-2-way valve, which means it has 4 ways and 2 ports. But that's just the technology. That's the terminology. But we start off with the way, then we say the number of position, and then we say way. Yeah, so the way. This is just the term. So if you went to order this thing, you'd say, I want a 4-2-way valve. And they would give you a 4-port, 2-position valve. And that's the terminology of the trade. You say, well, why did they do it that way? Well, I have no idea. That's the terminology of the trade. This is the way you order the part. So a lot of people will actually write it out because people have problems with it. So that valve was normally open. That would just change. Well, the symbol would change to this probably. Now, what you got to visualize in your head, is these blocks moving. So what I would do is when we move it, I'm going to come over here and I'm going to shift this thing that way. What you got to understand is you got to understand the blocks move. So if I put pressure on this side, the blocks are going to move. And now the arrow is lined up with torque. And that gives people problems too. So when we draw the valve, we show it in its initial or normal position. And then what you got to realize is that when I come over here and move that, the whole symbol shifts. Y'all understand that? So if I was to come over here and push on this side right here, oops. I'm going to come over and push on this side right here. Well, when I push out on that side right here, then this whole thing is going to shift over. So now my ports are going to be lined up, and here's my block right there. Because what did I do? I pushed that thing over that direction right there. So this is what gives people a lot of problems too, is they can't visualize that the blocks do move. So we draw them in their initial position, and then when we activate them or move them, the block moves. And then that's when the other ports start lining up. Are we okay? Well, what I did is I came over here and I applied pressure right there. Okay, so these two boxes are lined up, they're together, right? You understand? So if you come over here and do that, what's going to happen? These guys right here don't change. They're the ports, right? So they're going to stay there. So what happens is this whole thing shifts. And now when it shifts, what I have is here's my ports, here's my pressure port, here's my working port. So here this thing, now my fluid would flow through this and go out there and do whatever it needs to do. Right, you understand? Now if I come over here and put pressure on this side, what's going to happen? Well, it's going to shift back to that original position, and now the port is closed. Yeah, but when we draw it in its initial position. So this symbol right here would indicate this would be a normally closed valve.
So the arrow on the left box is basically like
no, it's representing a path that it can get through. These indicates a block path. So anytime I see that, that means that's a block path. Anytime I see an arrow, that means that is a path that can get through the valve. Okay. I understand. So here's my pressure down here, and here's my working port right there. What that means now is my pressure can come up and do what? Can flow through there. So let's go back and look at this, and this is very, very important, so we'll spend as much time on this as we need to push. So here's my pressure right here, and here's my actuator up here. So what's going to happen? Is there a path for the fluid to get through? Is there a path for the fluid to get through? No. So we got the what? We got the fluid blocked, right? So my actuator is not going to do whatever it's supposed to do. Yeah, because there's no path through. Yeah, see, there is no what through here. There's no path. So when I see this, it means the path is blocked. If I see an arrow, it means that we have a path through, right? You understand? So right now, if it's in this position right here, then what happens is my pressure is blocked, which is what we want on a compressor, right? You understand? Or even on fluid. So is this hydraulic or this pneumatic? Could be either one.
So to make it, to draw that out as an open valve, going to open, we'll cut the lines off over here on the port and draw them out on your arrow.
If I was going to change this to a normally open valve, then I would come over here and draw the valve like this. So this would be a normally open valve. This right here would be a normally closed valve. So here when I put, as soon as I turn my system on, I would have flow and I would actuate the valve to cause it to stop. Over here, we start off with the flow blocked, and how do I make it flow? Well, what I'm going to do is I'm going to leave everything alone. So this is my piping, this is my pressure, and what I'm going to do is I'm going to push that whole symbol to the right. Now, what's going to push that whole symbol to the right? Whether it's going to be done mechanically, it's going to be done manually, it's going to be done mechanically, or it's going to be done with a pilot valve with pressure, or it's going to be done electrically. Something's going to push that thing to the right. Well, this is what you got to visualize in your head is this whole thing is going to do what? It's going to shift over. Now, if it shifts over, the symbol is not going to shift in the diagram. You got to visually see that thing do what? Shift. You got to visually see that.
So where I'm trying to get in is here. The open is here. Close up if I need to move the block and line it up.
Need to move the block to line the arrows up. And when I move the block and line the arrows up, and that means we have flow in the direction of the arrow. Okay, does that make sense? In the direction of the arrow. So this would operate what we call a single acting cylinder. And what's a single acting cylinder? We've already talked about that. It could actuate a motor. So we could use this to turn a fluid power motor on or off, right? Or we could move it to come over here and we could draw the cylinder. So this is the way we draw the cylinders. And then we use this to represent the piston. And then this right here would represent the rod. And then of course what we would do is we'd come over here and put something like this in here. Oh, sorry. No. Good guess. It's a symbol for a spring. So what would happen when I shifted the valve from the left to the right, the cylinder would do what? Extend. And then when I shift it back, the spring would do what? Yeah. So we call this is most of your, your faucets, of course, those are, you can turn them all the way off or all the way on, but you can turn anything instead. That would be what we call a proportional valve, which we don't have in this class. This would be like your dishwasher or your washing machine, but everybody has a washing machine. So that's the type of, this is the valve you have in it. So either lets the fluid flow or it does what? Cuts it off. Check valve. So we've already talked about what check valve is. Check valve would be, a check valve has its own symbol. Two-way, two-position valve. So this guy is going to be self-activated, but we don't draw that symbol. So the check valve, this is the symbol for a check valve right here. So it's a two-position, two-port valve, but it's got its own symbol. Okay. And basically what happens is that if I put pressure on this side, can you see what's going to happen to the ball? It's going to sink the ball, right? You understand? If I put pressure on this side, what's it going to do? It's going to push the ball back. And that's actually that flow. This is a big way most check valves are made. I see them use slaps, but usually these balls are very, very popular. And either the check valve is going to be returned with gravity, or it's going to be returned with spring, or flow itself. So it could have a flapper. So the check valve on most compressors is a flapper. Y'all know what a flapper is? Yeah, so basically it's a spring-loaded piece of steel is what it is, or copper, or brass, and it's got a little overlap right there, got a little lip, and when it comes up, what's it gonna do? It's gonna open it up. When it comes another way, those are called flapper valves. Popettes, those are gonna be, huh? So you're getting.
Hey, that's the flapper.
Most compressors use little flapper valves. You ever look at a reciprocating compressor, and you'll see it's just got these little metal plates in there. It opens up one way to let the air in and closes off and blocks it and sends the pressure out. Check valve is very important. I guess that would be a check valve. Hopefully. No, I think that would probably, I don't know. I don't think. This is what we call a what? I don't know what this is. Yeah. So this is just another check valve. Lowest pressure that will open the check valve is called the cracking pressure. So there's another term. It's basically, it's got a spring on it. Huh? No, a pressure relief. The problem we have is that some valves, some of these check valves don't close. What we do is we come over here and we, or don't want to close. And then what we do is we'll come over here and put a spring on it. Well, let's say it takes 5 psi to generate enough pressure to put the spring on. Well, if you take 5 psi to put the spring back, you got 30 psi on the left. What's it? You get 25 pressure on those. So anytime you go to the check valve and spring, these valves that reseat them with a spring, and of course you're going to lose a little pressure on something. And that's what this next slide is right here. It's still filled in from the last time they taught the class. So all the pressure, this is, by the way, this is the symbol of a tank, of a this is one we use in hydraulics. So this is the symbol for the tank. And what's the function of the tank? Yeah, so we get the fluid out of the tank, when we pump it, and we bring it back. So this is another reason that hydraulics is so expensive, is that when you send that fluid out under high pressure, you got to bring it back. Now your return does not have to be, these could be low pressure pipes, right? The return can be low pressure pipes. But you still got to bring it all the way back to the tank, or the reservoir. So what would our pump, what would be the pressure on our pump? Let's push it again. This guy's dropping 5 psi, the other guy's dropping 10 psi, another guy's dropping 20 psi. So how much pressure would the pump be done at? So how much pressure do we have to send back to the tank? Yeah, 0 back to the tank, right? Because we're not pushing against anything. So to create force, we got to push it against something, right? So we have, basically, we consider the exhaust or the low pressure, the return to the 0 loss, even though that's not exactly clear. So how much pressure would the pump have to be? The answer is down at the bottom there. So what would that be? It would be generating 35 psi. How much pressure is the tank? How much pressure is the pump going to have to generate? Enough to move the load. So that means I got a pump out there that can generate 3,000 psi. It's only going to have to move a 25-pound load. But it's going to generate enough pressure to move a 25-pound load, right? So it's not going to generate that 3,000 psi. It's going to generate enough pressure to move whatever's required by the load, unless it can't move it. If it can't move it, it's just going to stall. That's another advantage that we have over fluids over electricity. Electricity actuators do not like to be stalled. They do not, especially motors. They'll burn up on you. I'll let you. Fluid power don't care. Fluid power, we can keep pressure out there, so I can, if I want to push something and leave it out there, I can leave it out there basically forever. It'll still generate the same one. No, yeah, you want to leave that pressure on there, yeah. But usually car lifts are either hydraulic or pneumatic. Most of them hydraulic. Because we want to use a small cylinder to raise up the car. So this is a good slide. I was wondering what was going on here, but that makes sense now, because all the four, what you have to do, either your pump or your compressor. By the way, this is what defines this as, I could take this same thing, this same symbol, and I can come in here and I can use a triangle that's not filled in. So this means pneumatic. If it's filled in, it means hydraulic. ULIC, or not. So that's the only difference between our actuator symbol. That's the only difference. Now your directional control valves are going to use solid lines for the air. So when we get into our actuators, if they draw a triangle for the inlet port or exhaust port, it's filled in, it's a hydraulic device. If it's not filled in, it's what? Pneumatic. So the symbols for motors, the symbols for compressors, these are all basically the same. How much pressure would this guy generate? It looks like that it would generate 20. It would generate more pressure, right? In fact, probably wouldn't. It would generate. How much would it generate? I was wrong with it. How much would it generate? Well, what's going to happen when that top one opens? Yeah, by the way, the top one, we would generate the maximum pressure of the compressor. The one on the right, the one on the bottom right, now notice they changed the direction. So the one on the left, the pump is pushing against a normally closed circuit, right? You understand? And it's seeding these things. So what's going to happen here is the pump is going to put out whatever it can put out. Now the one on the right, so we got one valve that will open at 20 psi. We got one check valve that will open at 10 psi. We got the last one that will open at 5. So what's going to do the pressure on the right? Okay. Well, all of it's going to flow through the 5 psi valve. So what's going to happen? That on the right is going to generate 5 psi. Because if that valve opens on 5 psi, then that's all the pressure that's in the system, right? You understand? Yes or no? Yeah, so here we come. Here comes this guy. He gets up to 5 psi. This guy here opens. Then now we got that path right there. So what's going to happen to these other ones? This guy's set to open at what? 10 psi. This guy's set to open at 20. They're going to stay closed because there's no way in the world we're going to be able to build a pressure system. Now up here, the pump is pushing against, it's going to close the check valve. So how much pressure is this going to generate? Well, no, it's going to generate whatever it can put out. Right. So if that pump can generate 1,000 psi pressure, that's what it's going to put out, whatever that thing can put out.
So with the spring on that valve on the one it's why is it allowing it, like you said, in part, it's just to be one. But if you were to run, how about it?
Okay.
All right. The spring is on the.
Yeah, so this is the pump side. So basically the pump is going to come over and go to there too. So it's sucking fluid out of the tank, coming up, pushing it here, right? So it's pushing this out, runs up against this one. This thing opens at 5 psi. Now if it opens at 5 psi, that means the psi across it's going to be what? 5 psi. Okay, if there's 5 psi right here, how can that get 10 psi right there since they're in the same line with each other, right? You understand? Huh? How can you open it up more than once that valve opens, it's going to drop 5 psi. Period. So how can I generate 20 psi up this line right here when I have 5 psi right there? What's that? How? So I measure that valve opens at 5 psi.
Adjust the pressure where.
Can adjust the pressure. These are, it's got 3 check valves up there. So y'all trying to figure out a problem that when we're trying to figure out, we've already got a solution, right? Of what the question is asking, right? You understand that? Yes or no? So what we're trying to do is we're trying to figure out the pressure that the pump's going to have to put out. Now, you're going to run into this in real life? No. This is just a scenario to make you think, right? You understand? So that means if I generate the pressure, these guys are hooked in parallel. So the pressure on this side, these is going to be whatever the pump out, and the pressure on this side is going to be 0 psi. Okay, you understand that? Okay, so at 5 psi, this guy's going to open, and now it's what? So what's the pressure that caused that to open? Okay, so can this guy right here open? Nothing else can, because as soon as that valve opens, then the two pressure on both sides is going to stay at what? 5 psi. So the other ones would never open. What you mean? Well, here we're pushing. Here we're closing the check valve, so we're pushing the ball into the seat, right? You understand? Okay. So we're pushing this one. This one is set for 5 psi. This one is going to open at 20 psi. This is 10 psi. This is going to open at 20 psi.
It's gonna open it.
Well, no, it's going to when you get the rating of a check valve, it's what pressure is required to open. Right? You understand? So I'm pushing this into the seat. So even though this guy is saying, okay, if I see 5 psi pushing from this side over here, I'm going to open. If I see anything pushing from this side over here, I'm going to do what? Close. Okay. So what's going to happen here? So how much pressure are we going to have on this side right here? Whatever the system's putting out. No, we're seating the valve. No, we're seating. Look at this. So when I push this thing in here, this is going to turn the valve off. So look, the pressure on this side is going there. What's that going to do with the ball? It's going to cause the ball to seat. If the ball seats, it's turned off. Okay. So I'm out there running my hose, and I turn this guy off. No, well, we're not getting any pressure out the end, but now you're getting the maximum pressure of whatever of your system, right? You understand that?
When it's flowing,
But I come over here, and I got this valve over here, and I'm turning this guy here on, and it's got a back pressure of 4 psi. I come over and turn this guy on. This guy over here might not even work because it's not seeing any pressure, right? You understand that? So what you got to do when you visualize the check valve, if we're pushing the ball into the seat, it's going to do what? It's going to close it, right? If I push it away from the seat, it's going to open the valve. So over here on the left, all these are pushing it into the seat. So how much pressure are we going to get? Whatever the source can deliver. Over here on the right hand side, now we're using the same valve that's got the same amount of opening pressure, right? You understand that? As soon as that one opens, then all the rest of them are not going to be, we're going to have 5 psi across those two lines. Now here they're hooked in series. So here, to open all these valves up, what would I have to have over here to open all these? Not on these guys. Not on these guys. Yeah. So what are we gonna need up there? No, what are we gonna need up there? What are we gonna need up here? Okay, let's look at the valve. Let's look at the ball. Is the pressure on the pump seating it, or is it pushing it out? Okay, so what's going to happen? It's going, yeah, and we're not going to get any pressure down the system, right? I think I did that wrong a while ago too, guys. What are we going to get on the bottom? Got to get at least 35. So as soon as we get 20, then what's the second one? 10 and then 2?
I got a question on the valve. Oh, you really need pressure because I mean, there was springs up there.
All we're doing is just trying to figure out, in this example here, we're trying to figure out if the dang thing is open or is closed. If it's a spring actuated valve, you have to exceed the pressure of the spring before it's open. Okay. Well, that's what we're trying to do here. We're not trying to figure out what we need to do or what we're trying to do. All we're trying to do is say, okay, if I can understand these, then I have a real good feeling of a check valve, right? And what does a check valve do for us?
Make sure it's going
one direction. It prevents it from going the other direction. So we'll use check valves. We're gonna use some,
Particularly when it sits there, so you don't use pressure. Spring.
on this one,
On
no.
this type of spring.
And that's why, so this one would close even if you didn't have any back pressure. That makes sense? I got a check valve, on my, shop bag. My shop bag has a check valve on it. What they use it for. If the tank gets full.
Blowing it out.
Shuttle valve. So this is the shuttle valve that I was telling you about. So shuttle valve, this is basically a valve that is self-activated. And it's usually a 3 or 4-way valve. But what we do, it permits flow in one direction, whoever does it first. Make sense? This is what I was talking about, where we have 2 operator stations for control and actuate. And we don't want those two right? We don't want 2 people trying to do different things with the same valve, same actuation. So what happens with the shuttle valve, when I come over here and I open my valve, it automatically pushes that shuttle over to the other side, and what does it do? It closes the other side, so now the operator can't do what? Can't open. And then when I come over here and turn mine off, then what can the other operator do? The operator can close. So these are basically safety devices. I think we went through our break. All right, let's take a break, guys. 2 minutes. Who came in? James and Alfonso. Okay, this is a symbol of a shuttle valve. So one of the big things y'all gonna have to learn how to do, of course, is to learn these symbols, right? So let's look at these symbols up here. These symbols on the left, these are pneumatics. Because, so if this was going to be, normally what we do, guys, is that we don't draw the pump. We don't draw everything. What we normally do is we use this arrow, this big arrow on the outside, the big one represents the pressure point. Here, this is pneumatic. How do I know it's pneumatic? Not just because it says air, because it's not filled in. Right? Don't understand that. If this was filled in, it would be what? Hydraulic. Okay. So what would we say about that top one up there? This one right here. Two positions, right? Okay. Well, 2-way, I see 3. One, two, three. See? Yeah. So here, this would be 1. This would be 2. This would be 3. So it'd be a 3 2-way valve. Right? See that? 3 2-way valve. We'll start off with the wave, then we go to the position, and then we say, well, manually operated. That's the symbol of an operator. And this other one on the same side, the other one would be the same thing. 3 2-way valve, manually operated. This little knob right here, see it looks like a handle. So if we draw this, then let's just look at this one direction. So this is in its normal position. Here comes our airflow right here. And it's sitting here and it's blocked off. Right? You understand? Then I come over here and I use this operator to push it in that direction. What's that going to do? It's going to move this down to here. It's going to come up and do what? Yeah, and this guy over here now, as soon as I take control over here, this guy over here can't do anything because that's what the shuttle valve does, right? What do you mean?
Three, especially the top and
No. This is the shuttle valve right here.
Oh,
So what happens as soon as I connect this air brings it over, brings it out. What it's going to do is it's going to come flowing through here, and it's going to push this into the sea. Okay. Now this guy will go over here, and he wants to do something with it. You can't do anything with it because it's a shuttle valve. So what the shuttle valve does is it lets us have two operator stations at different locations. But the first one that uses it is the one that has control. Right? Does that make sense? These are, so this would be what we call a rotary valve. So how many ports do we have here? 4, right? Positions is hard to see. I think it gives us the position. So this would be a 3-position valve. 4 3-way, right? But we wouldn't draw it as this. We would draw it as this symbol right here. So what I do is my valve would have 3 positions. Okay. And what we would do is we'd figure out which direction this goes. That's just hard to see. Neutral position, return position. So this is this guy right here. So what this would do is it would be like this. So notice in the neutral position or the center position, everything's blocked off. There's no fluid flow, right? Now they say this is the feed position. So this is going to come in through C. It's going to route it through 1. And we can draw this different ways. And then this is going to go back to the receiver. So I come up here and do this. And then my other one would be drawn like this. Can you see that? Normally, on this one, this is not exactly true. Normally, on a 3-position valve, normally your center position is what they call the neutral position. So normally your ports would be put right here.
this thing for you.
What do you mean?
It's what having the circuit. Count that over. Count that.
No. In position, in electricity,
Well, I mean, you have like a switch that you like.
we don't call it, we talk about 3 position, electric switch, center off. Yeah, it would be sort of like that. But we're not changing the direction of flux. I guess that could be that. So normally when we have a 3-position valve, the center is considered to be the initial or the neutral position. Can you see that? So was it was the one direction that would let the air flow, and then when we shift it in the center, it's going to block it, right? If we shift it over again, it's going to reverse it. These are the valves we have, we'll call spool valves. And I guess it got the name of a spool because when we look like this, it looks like a spool that comes on the bridge. But what we do with the spool valve is we come over here and we change the position of the spool. So this shows the port aligned up with the arrow. So remember, the port is drawn in its initial position, right? So they're putting it on the left here. So what would this be? This is going to be a 2 position, right? How many ports? 2 position. It's going to be called a normally open. Because when they draw the valve, they draw it in its initial position. Now we move down to the one on the bottom, which would probably be, so all we're doing here is we're drawing what we call the valve. And these that here are going to be our operators. So here's the valve. And these are our operators. What's this a symbol for? Spring. Not quite. A cylinder would be this. So a cylinder would do this. This is the valve. So this is a manual operator. This is another. This is like a push button. So I come up here and I got a knob. I push in on it, and it shifts the position of the spool. And then when I let go of it, what happens? Comes back. Guys, I wish I wasn't texting me that kind of stuff, and it bothers me. I hate to think that I'm boring. I think y'all got more important things to think about than. So if you need to text or talk on the phone, that's fine. But what I want y'all to do is just get up and go out here. Don't bother me in class if you don't mind. So I know texting is real neat. Okay.
I like it.
Huh? Well, texting's needed that you can do it in meetings and stuff like that. So 3-way valves. So let's do these are 3-way valves. They can be either 2 position or 3 position. And so we have different, we call them centers. You got different centers. That would be that center down in those 3-way valves. Those would be those different centers you can do to get different features out of the valve. So what would that top one be? So let's go 3 2-way, manually operated spring current. That's what we say that valve is. Manually operated spring current, right? Or actually, let's leave it. So all we're doing is we're shifting the spool. The one on the right would be basically the same thing. It's just that P stands for what? Pressure. E is what? Exhaust. In hydraulics, that would be a T for water. Tank. So pneumatics, we call it E for pressure. And then your working ports. So on your pressure side, we're going to have 2 type of ports. We're going to have an exhaust port or a tank port and at least 1 pressure port, right? You understand that. Then we have what we call the working port. The working ports are usually A, B, like that. Now, when we number them, I'm going to have to go ahead and figure out the numbers. So when they number the ports, the pressure port is always number 1. And then you jump up to the top, you say 2. Your exhaust port would be 3, and your other working port would be 4. So your even numbers are going to be working ports. They number them. Your odd is going to be pressure and tank. That makes sense? Those kind of words. So we go 1, if it's numbered, 1 is always the pressure port. If they give them letters, the pressure port is going to be P. And then your exhaust port will be E. Your tank will be T. And then your working ports are going to be A and B. Make sense? Trouble is, most of the time they use numbers and they don't use the P's and the A's. You see it every once in a while. But odds are when you go over there and look at our valves, they're going to be 1, 2, 3, 4, I don't know if we got any 5-port valves or not. Usually, if we're using it as just a directional control valve, if it's got 5 ports, all that means it's got 2 exhaust ports. I got an additional exhaust port. Are we okay? So down at the bottom, what would this be? The one on the left, this would be a, yeah, three-way. Lever operated center, spring center. So that means if you let go of that handle, that lever, you let go of it, it's going to automatically shift back to the center position. And then you shift it. You can shift it to the left, you can pull back, shift it to the right, and when you let go, it goes to the center. And this valve right here would be closed, not unless you're on the one on the right. So we would, the one on the left, we'd say that would be, we call it a normally closed center. The other one, we'd call it a normally open center. Some people call it. Now notice the pressure's on the top, so that's a normally open center because it's got the pressure where? Up top, yeah. So we'd say that's a normally open center. It's always holding pressure. It's not flowing, it's holding pressure. Because as soon as your actuator moves, you have flow. Right? As soon as the back actuator stops, then you don't have flow anymore. But you still have what? Pressure. Still have pressure. So what would happen on the top one is it would lock the cylinder wherever that cylinder was at. On the one on the right would be locked. You couldn't go up there and do what? You couldn't move. It's got the same pressure. It's pushing on the same pressure on both sides. So if you're pushing the same pressure on both sides, then the cylinder, the actual piston would be locked. So we have floating cylinders, we have tandem centers, we have open centers, we have closed centers. So we have different centers depending on the application that we want to do. We center, right? So like normally on a hydraulic system, if it's the only actuator in there, and I come over here and I let go of it, I want to return pressure back to the tank. I don't want it to have pressure. Flow's okay, right?
The one on the right, pressure at the top, so you close off
Well, if you shift it to the right, so I think, and I shift it to the right. Yeah. Now normally this guy is not drawn right, and I'll tell you why. Because standard practice, I can show you all type of diagrams, and normally it's just like schematics over here in the good old United States. When we do electrical schematics, we go from left to right. So your inputs are always on the left, and your outputs are always on the right. Now, fluid power, we usually draw them from top to bottom. So normally your pressure port's on the bottom, and your working ports are on the top. And that's what, for me to show you all that, is to actually show you some true pneumatic print. So we'll be looking at these during the semester.
All of those are three-way notes, like that one that had a C on top and the A and B. That's a three-way.
Yeah, those three ways. Yeah.
Well, I know that A and B is
Hold on, let me think about something. So there's pneumatic diagrams. So you can see the valves. These are all what? Every one of them, same valve. It would be all 4 two-way valves, right? Four two-way valves. Right? They're all 4 two-way valves. The little rectangle with the slash through it, that means they're solenoid operated. with a manual override. A lot of your valves have a manual override. So solenoid is electrically operated, but you lose power and you need to go out there and move something. We have the ability to manually override. Spring return. Then these are single acting cylinders. These are double acting cylinders up there. And what do we mean by double acting cylinder? We use pressure to move them both ways. So a single acting cylinder, what we do is we use pressure to move it one way, and then something else brings it back, either gravity or spring, right? A double acting cylinder, we use pressure to extend the rod, and we use pressure to retract the rod. So those are single acting cylinders. The guy right here, by the way, this is the Ventura. So what that's doing is that's a vacuum generator for us. This is a service unit. So this is a filter. This is a pressure regulator. What would y'all think that is? What do you think that's a symbol for? Pressure gauge, yeah. And then this is what we call a manifold. So what the valves actually come in and share the same exhaust. So this is the exhaust port. This is the port. This is the exhaust line right here, and then this is the pressure right here. But notice what they do here. They don't call them P. They call them 1, 2, 3, 4. Look how they do it. So the pressure port is always port number 1, right? Then your first working port would be 2. The one on the pressure side, even though your exhaust would be 3, and the working port would be 4. And if I had another exhaust port, it would be 5. So everything on the power source side, these are odd numbers. Everything, all the working ports are going to be what? Even numbers. And of course, we'll only have 2 working ports. Huh? Yeah. All we need is 2 working ports, because what can we do with an actuator? We're either going to do what? We're going to extend it or retract it, or we're going to run a motor forward, or we're going to run it reverse, right? That's about all we can do. These are, we'll look at these later on. Of course, we know what these are. What are these? No, this right here. What? These are little check valves. All right, that's what they are, check valves. All we got to do is figure out what that on the right. This is the solenoid right here. This rectangle with a dashed line through it like this. This is the solenoid. So what we do is we electrically move it one way, and then the spring does what? Pushes it back. But I have a manual override, so that means if something happens, and I can go over there and push down in that little, and by the way, it's usually recessed. You usually have to have an Allen wrench or something to push down on there, because they don't want people just coming up there pushing buttons, because that could be dangerous. And I tell the story too. We had a guy killed out of U.S. Steel because the guy went in and manually override and pushed in the wrong thing. You need to know the consequences when you use the manual override. So, but this is so notice we have actuators, and this is pretty standard. So each actuator so the whole circuit is labeled 1. So that would be actuator 1. And notice everything that belongs to actuator 1 starts off with a 1. 1V2, 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 1V3. Then we go over to the next actuator. It's called 2A. That's the actuator. And everything that controls that circuit starts off with a 2. See what I'm talking about? The third actuator over there, they're calling that actuator 3A, or the third actuator in the circuit. And notice everything that belongs to that actuator starts off with a 3. So it'd be real easy for me to identify what valve belongs to what actuator if I had the diagram. But this is the way we draw a fluid power, is our power comes in from the bottom and the actuators are on top. So this is normal way. So that's why I wanted to show y'all this, to actually show y'all a diagram of a fluid power schematic. And we call these schematics. So this is drawing kind of weird. So notice on the bottom ones, they're putting the pressure on the top, and so we wouldn't normally see them drawn like that. Normally the pressure would be on the bottom. The pressure ports or the power ports are going to be on the bottom, and what we call the working ports are going to. So the working ports is the term we use for the ports that control the actuator. Are we okay? So the circuits that we hooked up are going to be drawn that way. And when you do your circuits, you're going to have to draw them. So power from the bottom, actuators at the top, right? And then control is going to be in the center. That's the industry standard. And y'all going to have to do that, guys. Y'all going to have to design some circuits in this class. Yeah, so the control's in the center. Power's on the bottom. Control in the center. Actuators on top. And that's standard for drawing. Electrical schematics is power's on the left, right? So everything flows from left to right. This would be a four-way two-position valve, two-way valve. We run that, so every one of these on that diagram that I had was this valve right here. So what does this guy do? Well, it's going to push something in one direction, and if we shift the spool, it's going to shift it in the back. So this is a true directional control valve. So it's controlling the direction of the flow. And then what we do, we add other things to the symbol on how the valve is operating. Right? You understand? We put these on the outside block. So this is just the valve. This doesn't show us how it's operating. So something's got to cause that spool to shift, or something's got to cause that rotor to move, or something's got to cause that disc to move, right? Or something's got to cause that ball to move. So this would be what we call a double acting cylinder. Don't understand that, right? Understand that now? So what's a double acting cylinder? Yeah, it moves it in both directions. Right. Single acting cylinder, we use pressure to move it in one direction, and then something else is going to cause it to come back. Yeah, good. So this would be how many, so here, notice they show the exhaust ports on both sides connected together. So basically a 5-port valve, you'd have 2 exhaust ports. And so it would be able to exhaust a lot faster. Here, the 2 exhaust ports are actually connected together to an internal tube that's inside the valve. So all we see 4 ports. And actually there's how many inside the valve? There's 5. So a 5-port valve, what they do is they just bring out instead of tubing that inside the valve, they actually bring 2 exhaust ports out. Are we okay? So this would be a what? Or two-way valve? Commonly used in hydraulics and pneumatics. So the valves that we've looked at is basically the same for hydraulics or pneumatics. The only thing that basically changes is what we do on a 3-position valve, what we do with that center position. So we have different types of centers that we have. Are we okay? So this would be a what? 4 3-way valve. And this would be what we call a closed center. Huh? Well, we don't call it a normally closed. We call it a closed center. Well, we don't let anything move when it's in the center position. Normally closed and normally open, we usually use those terms for 2-position valves that either are normally closed or normally open. When we get into these, we talk about the center, right? So we say this is a closed center. Now, what is a closed center? So, yeah, there's no flow in the center. So what would this do? Well, it's going to hold pressure, for one thing. So we use this a lot in a pneumatic system. It's going to hold pressure, because we don't want to vent our compressor when it's not being used, right? So we come up here and we'll close that center off, and we can't move the actuator. Why can't we move the actuator? Huh? Well, the pressure is the same on both sides, and so what happened is I've got that center, and there's no way that the fluid can flow. So let's say this guy's out in here somewhere, and I've got this guy blocked off, and I've got this guy blocked off. Well, see, there's the fluid can't do what? It can't flow. Now, compressed air, we might can move it a little bit, but if this was liquid, you would not be able to move that actuator. So we can literally lock an actuator somewhere between extending and retracting just by blocking the two working ports. By blocking the two working ports on a liquid, it stops right there. So we can stop these cylinders anyway. Pneumatics, we might be able to move it a little bit because the exhaust port might be uncompressed a little bit when we block it off. But we're not going to be able to move it very far. So this would be a what? This would be a 5 3-way valve with a low pressure exhaust and a high pressure exhaust. I've never seen one of these. I've seen 5-way valves, but normally what they do is they just have 2 exhaust ports on them. So this has a low pressure exhaust and a high pressure exhaust. I don't know what that is. So here's some of our valves. So the first one would be what on the top one? Yeah, but we start off with 2 2-way, right? Then we say this would be normal flow. The next one would be what? Normal load. The next one would be a what? 3 2-way, right? Then we would have the next one would be what? 3 2-way, open normal position. So here we're talking about a normal position. So that would be your initial position that the valve is in, right? The next one down on the bottom left, closed in the neutral or center position, right? Understand that. Then we get into directional control 4 2-ways, right? 4 3-ways with a closed center. Most people, I've heard them call it center. The bottom would be what we call a 4-3, exhausted neutral. And you'll see how that works. So what would I be able to do on that one in the center up there, the one on the bottom, the second, third one from the top? What would I be able to do with the actuator on that one if it's in the center position? Huh? Stall it? No, stall it, not this one. We're looking at this one right here. This guy right here. Yeah. What would we be able to do with the actuator in the center position? You're gonna be able to move it, right? So I come over and push it. It's gonna exhaust it. I'm gonna push pressure on this side. So some people call this a floating center because I can actually move the actuator. The actuator actually floats. Yeah, because both sides are exhausted. Right? You understand that? Then we have what we call a 5 3-way. Sorry, a 5 2-way. And then we have a 5 3. So, but notice what they do. We need to bring up that. So we have 2 exhaust ports on the bottom. That would be 5 and 3. But where do they put the pressure at? They put it in the center, right? They're the ones in the center. And these are just some of them, guys. I don't know if I think the PowerPoint shows you. And when you start looking at these 3 position valves, this is what changes. The outsides are a lot alike over there, but when you get into those center positions, those are the ones that you get different things. We have what we call tandem center, specifically for a tandem center. No. So let's continue on. A tandem center would have the bottom one, it goes from pressure to tank, or from pressure to exhaust, which we don't see much on pneumatics. So we don't want to vent the pressure of a compressor to the outside air all the time. Why? Because we lose our compression. Now your hydraulic pump starts heating up when you make it develop pressure all the time. So what we like to do on a hydraulic pump, if we're not using it, we want to send that flow back to the tank, right? On a pneumatic system, if we're not using it, we want to keep the pressure out there. No, those are directions that we can move fluid. The cylinders are up here on top. I showed y'all the schematics, right? Did I close them out there? I bet I did. So the arrows are not the cylinders. The arrows are the directions that the fluid controls through what we call a directional control valve. So this is the path that the fluid can flow depending on what position the valve is in. Right on that. The actuators are on top. So here's my cylinder right here. Oh, I can't draw on that. It's not a PowerPoint. There's my cylinder on the top. This is a PDF file. So my cylinder, so don't get confused with the arrows. That's not the cylinders. That's the direction that we can do what? That we can flow through the valve. And you can really see why these are called directional control valves. So what's the three things a directional control valve can do? It can stop the flow, open the flow, or it can change the direction of the flow. That's the three things it does. That's what it does. It can open the flow, close the flow, right? Or change direction. That's what it does. It's got, what do you mean? Oh, it's got 1A, actuator 1A. It's called the feed stream. It's a double acting cylinder. So a double acting cylinder means what? So you're looking at this. This is the actuator. This is one circuit right here. Okay. Here's the actuator for the circuit right there. This is what we call a double acting cylinder because we use pressure to do what? Extend it, and we use pressure to retract it.
That's not a cylinder over there.
This is a cylinder right here, but that's a different circuit. That's a completely different circuit, right? It's like my house. My house has a lot of different circuits on it, right? You understand? So you got your, so this down here would be like your panel box where we distribute it out. We call it a manifold right here. And then we come in and we attach different circuits to each one of those breakers, right? You understand? Well, this right here is an individual circuit. And what makes up a circuit? Pressure source, control, load. And then we have to have the conductors that connect the circuit together. Okay. Of course, here we call that piping. And in electricity and electronics, we call them conductors or wires. We call them wires. Those are used interchangeably. So here we have 4 different circuits that control this station. So if you looked at the Amatro line, it's set up in different modules. So most manufacturing plants have different departments that they have. And then each one of them they might share a power source, or and then we have the diagrams for that section, right? You understand? And then one section feeds the other. This is only one module. I don't remember. This is the module 1. So this is the one they call the pick and place, I think. I'm not sure. But we can look at the diagrams for the Festo line, and they're going to be almost identical. So this is the standard for drawing these things. So power's on the bottom, actuators on the top, control is in the center. So I don't know exactly what this is right now. Well, I do know what this is. I know this is the what. But I don't know what this is. James already knows. Well, it's not. It's what we call a flow control valve. So notice it's got the air in this is true in our tray too. If you see an arrow drawn through something like that, it means it's variable. It's adjustable. So that's what we call a flow control valve. Yeah. Well, someone's got little handles on it, which is dangerous for guys, by the way. It's in our genes. So we had a group come in from Bros the other day on our manufacturing line. And, they told the guys it was a photo op. Bros we have an internship set up with Bros. Bros makes basically seating and stuff like that for about 3 or 4 different auto manufacturers. And they said make it look like you're doing something. You know what they started doing? Turning knobs and flipping switches. It's just in our genes. Guys, it's in our genes. If we see a switch on the wall, what are we gonna do? We're gonna flip it. Yeah. Let's see what this does. We don't say, well, somebody tell me what this does. Let's see what this does. So we get on to the right-hand side over here. So now we get what we call a service unit in pneumatics. A service unit usually consists of a filter. It consists of a pressure regulator. And it consists of a gauge. Now in pneumatics, when we compress it, what we do is we don't have this problem with most hydraulic systems because most hydraulic systems are oil. And what advantage does oil have in using as a liquid? Huh? Huh? Well, any liquid will. I could use water. I could use water in a hydraulic system. I could use water in a hydraulic system, but water basically contains no lubrication. So that means that will get us a problem right off the bat with all these cylinders and everything out there trying to use water, right? Now, we do have people that do. There are lubricants that we can mix in water. Well, soap and water mixes, right? So there are some lubricants that you can put in water that do mix. So we've got waxes. So you can get waxes that you can put in water that normally wax don't mix in water. But we do have waxes that we can put in water that they mix together. I mean, that's a good question. I mean, it's used all over the place. I mean, but I wouldn't use it in, I'm not going to use it in huh? In an industrial environment, you're not, unless that's the only thing you got to work with. If you're in a, and what advantage would water have over other things? Very cheap. Yeah, I wouldn't, of course. But the problem we have is it varies a lot with temperature, right? It expands when it freezes, and so if I let it freeze, what happens if you let your engine block freeze? You got a cracky block, so we put antifreeze in there just to change whatever they call that, the freeze temperature of the water. Waking up. I'm not asleep in my class.
Oh, on that, my eyebrow.
Ask everybody in here to take a look. Huh? What you mean?
Yeah, those other ones wasn't in that slide.
Yeah, I don't.
Well, they must not have.
Like that one.
Yeah, guys, y'all got to interest. This is not a class that I usually teach, so I'm not responsible for this slide. And what we do when we teach a class is we copy the last time over. We copy it the last time it was taught. We copy it over. And I don't go into it. I don't check all these PowerPoints. I don't check all this stuff. Why don't I do that? Well, no, because I'm already maintaining 5 Blackboard sites. So if you let me know that these are not up to date, I will update them, believe it or not. Yeah, and like I said, just because it's on these slides don't mean it's the ones on Blackboard. It's whoever taught the class last, they were responsible for doing it. And if you don't tell me there's something wrong with that Blackboard site, I'm not going to go out there and check everything. You know, I do 5 classes every semester. Okay, so thank you. So I'll go out there and I'll put them up. All you gotta do is say, well, these are not on there. So I was going to explain why sometimes this is not on there. So I'm not trying to be smart, guys. So I'll update it, but I can't do it now. Are we okay? So this is not up there?
Yeah, that one's up there.
This one is?
One of what?
I have no idea what this is. This one up there?
But it was
This
the
one up
one
there?
before that one that had 12 set up and like that.
This one's not up there?
No, that one's on there.
Well, it don't make any difference.
13.
It don't make any difference. What I'll do is I'll upload these slides. So I'm not going to figure out which one's up there and not up there. Are we okay? So I can use one unit to represent the host service unit, which would be the top one. And then this is different things that can make up the service unit. So the second one from the right, what's that one? That's got a what on to start off with? It's got a filter, and it's got a regulator. So normally we want to, if I'm going to calculate how much force I'm going to do, then we don't want to leave that force up to the pump. What we want to do is we want to have a pump that puts out all the pressure I would need, and then we need to set the pressure for what I want, right? Does that make sense? So pneumatic and hydraulic systems is about all have what we call a pressure regulator. So that way our compressor or our pump could put out more pressure than I need, and then I could set it to what I want. So normally commercial grade air tools are supposed to be run at 60 psi. So most of our compressors are not continuous duty compressors. They're not continuous flow. What do we do with most compressors? Pumps up to 100 psi, then it shuts off and it drops down to 70. Then it fills back up. So that means if my pressure tools are rated at 60 psi, as long as I'm not exceeding the flow rate of my tank, if my tank can hold enough air, that means I'll never get below what? 60 psi. So we're okay, right? You understand that? And the same thing's true on my hydraulic pump. So we want a hydraulic pump to put out more pressure, and then I can regulate it to what I need. So what's the disadvantage of running something at lower than a required pressure rate? Yeah. Well, that means all your calculations are out the window. So if you're lower pressure, you're not creating the force that you wanted to create, right? You understand? What's the problem with running things above the rated pressure? You start breaking them, you start busting seals, you start messing things up, right? So under pressure means you're not going to generate the force that you wanted to generate. Over pressure means you're going to tear everything up. So I've seen people run their dang impact wrenches to run them wide open. They turn their pressure regulator all the way up, and they wonder why they keep blowing up seals and having to replace them. These things aren't no good. They keep tearing up on. Plus oil, a lot of times in oil, we got 2 robots over there that the directional control valves get locked up on them because they're not self-lubricating valves. So our compressor has no lubrication in it. So we can have what we call oilers, which basically just do what? Just squirt a little bit of oil in the air every time, and so we've got some lubricators. We just hadn't got time to put them in there. But if you ever went and looked at these big old robots, you got to lubricate those things. So you'd see those things have lubricators. So we don't have to do that in hydraulics because most of the time the fluid itself has got lubrication. But if I was spray painting, I wouldn't want anything. I wouldn't want water. I wouldn't want oil. I'd want some way to get rid of the moisture, but I wouldn't want to put oil into my spray gun. So service units have different features. Just about all of them have start off with a filter, and then most of them have pressure gauges on them, especially if they got a regulator. It wouldn't do me any good to have a regulator without a pressure gauge somewhere. So these are the symbols. So filter with a water trap. Filter with a water trap, automatic release. So a lot of them's got a little thing on the bottom that you just turn and release, drain the water out of it. In fact, we saw that. I didn't last time I taught fluid power. The whole compressor tank must have been full of water because when we turned on the pressure, water started squirting out of these up on the top. So we'll need to go in and drain that. The one over in the hall building has a automatic drain on it. So every once in a while you hear there by itself, and what's it automatically do? It's bleeding that water off. Mist separator, I've never seen one of those. Water trap, automatic drain, seen those. Haven't seen a micro mist separator. Have seen lubricators. Dryers, we have dryers. We'll look at some of those. So what we do is we basically get rid of the moisture before it gets out. All these dryers. And then coolers. Cooler is a method that we can do to get rid of water too. And get rid of air. Because if I expose air to a cool temperature, then it causes the water to condense. So we have the chillers or coolers. These are our operators, guys. I know it's been time to go. I know y'all get. So these are our manual operators. Y'all see those? So hand lever, cam operated, solenoid operated. These are our, it says actuators. I don't like using that term because we call our cylinders, we call them what? Actuators. So where did it go, Rich? So what we'll call these operators. Which is what they are called in. So hand operated or lever operated, cam operated, solenoid operated, manually operated, that's just a generic, spring operated, pilot operated. What does that mean? Pilot. What does pilot operated mean? That's a shuttle valve. What does pilot operated mean? Well, this would be hydraulically pilot operated. Now this would be electrically operated. Right? Pilot operated. Huh? I know it's a long day for you. So we actually use the fluid pressure itself to change the valve. It don't make any difference. We use the pressure change to change the valve position. So I could come over here and I could I could use this, and then I could take this out right here, and then I could run it into one of these. So what would I have is I'd be using this little valve over here. I could either manually operate it or I could electrically operate it. And then I use the pressure out of that valve to change the position of this big valve. Now this has done a lot into a pilot because we get to 3,000 PSI, right? Understand that. And I'm trying to do a flow rate of 100 gallons per minute. The valve is going to be this big. And I cannot manually operate that valve. But I can come down here and have this little valve down here that I turn that 3,000 pounds of pressure up here, pushing against the air. So up here I can take that 3,000 PSI, which I can't move, and I can run that into a 1 square area spool in. Now I've got 3,000 PSI to move the spool. Right? You understand? So these would be what we call pilot operated valves. A lot of times the control valve is mounted on top of the pilot valve. They're right there together. And then I can shift the spool with a solenoid. The solenoid can't generate a lot of force, but it can generate a force to move the small valve, and then the force coming out of that small valve can move the water, can move the big valve. So we have that. We have pilot operated valves built in. I'll try to bring one over here and let you see it. To generate that, for me to generate that much force to change the spool. So you got to be able to push that spool against that pressure, right? And the spool's got surface areas in there. So you got to be able to move that spool against that, control that pressure. It's just like me out there on my hose, when the hose is turned off, it's real easy to move that thing. You go in there and turn that thing on, now it's all of a sudden it's harder for you to control that flow because now you're trying to open that valve up against pressure. So this would be pilot operated. So a pilot operated valve, we literally shift the spool or change the position of the valve would probably be more correct. We change the position of the valve with pressure. And then we use something else to control the pressure, right? So we have pilot operated valves that we're going to run into, but we'll have a little valve down here I'll flip with my switch, and it's going to change the direction of flow, and that's going to shift the valve. You probably know enough about this now, because the only cylinder we're going to do.
The pilot valve, like in the gas, you got a little flame that's always different.
Yeah, so they call that a pilot light.
Right.
So you're exactly right. So you got this little flame, and you use that to light the big flame. And then what do we light the pilot light with? Well, it depends. If it's a water heater, it stays lit all the time. If it's a heater, it's got a little spark plug. It's basically nothing but spark plug. Yeah. That's basically it. So guys, I think this is about it. Let's, one more thing. These are different centers. And like I said, you could talk about centers all day long. These are the different centers that we could run into on a 3-position valve.
So, worksheet, we got to print them out and have it or
What's that?
the worksheet on it?
Yeah, there's supposed to be worksheets. You don't have to normally print. A lot of people don't have printers. We got a worksheet on every chapter. So what we normally do is give you 7 days to finish those things. 21 to finish up an item. You don't have to print them all, so you can just bring them up on the screen and answer the questions. Just make sure you put the question numbers.
Okay, question number.
Yes. What's that? No, these are just worksheets that's on there. I better save that because I made a lot of changes to it. Didn't I? And now this afternoon I'll go up there and I'll upload the new version. Oops. I'm listening.
I was looking at what those sheets are.
They're in industrial pneumatics, and then when you go to course content, worksheets and quizzes.
Oh, okay.
Worksheet 1.
We need to do one.
Yeah. Yeah, I need to figure out. They don't look like they're in the right order today. Yeah, so this was worksheet 1.
That would be covered with the information chapter 1.
Yes. So I'll go ahead and put this on the calendar. We'll make it due Monday.
No, I'm gonna go with
Okay, guys, we're through.
you.